yet another day of our training. I'm sure we are all geared to learn more and eager to learn more. Thank you for hanging in there and learning more on data presentation and also a bit of interpretation. I was hearing Professor Balaba yesterday. She was going through those components in data interpretation and analysis. So I would like right now to hand over to our facilitators, Professor Balaba and Dr. Namaweji. Professor Balaba, over to you.
Thank you very much, Dr. Runyararo. Good morning, everybody. I hope you are okay. And we want to finish a bit of ANOVA and go into regression today. So we'll do a bit of ANOVA and then we'll let you do ANOVA with Dr. Helen. So the first thing we are going to do is let's see those who received the exercise. If anybody is ready to present for us, we will request David to choose whoever puts up their hand first to present the exercise we did yesterday. I gave you a short exercise last afternoon, yesterday, and I'm requesting anybody who did the exercise, you can volunteer. You can volunteer. Yes, it is cold here in the room where I am. You can volunteer to show us what you did. Anybody ready? You can raise up your hand or use the chat. David, are you there?
Yes, here I'm promoting them.
Okay. Whoever raises up their hand first, you choose them.
Yes, now we have Dennis Wamalabe. Please go ahead.
Hello, Prof.
Can you zoom in?
Okay.
Another time. Okay, go ahead.
Okay, now good morning, everyone.
Good morning.
So on this app, just to raise the hand because I tried to do some of the work, but I didn't manage to do everything. So I will show you what I did. And because I'm an amateur in this art, so you'll guide me.
Okay.
Yeah, so I start by establishing my directory here. So I think everyone knows how to import to get to set the directorate. Then this is my data set importation, and I named my data set as germination.
Okay.
So I created the vector as seed, and then I read in CSV. So I viewed, so I can just want to show you this is how I arranged my data now. This is the column for treatment and germination. That's the treatment method, A to O to D, then the what germinated. As also part of getting to the descriptive statistics, I just ran the structure for the data, and you can see. And then maybe on the summary is when you shall get to see more. So this is the summary of the data that I ran. And this is just part of the descriptive statistics. And now to move ahead to get to see the seed treatment as a factor, I created a vector of germination. Then I read treatment as a factor, which I also ran. I can also show you that. So the summary is here. That's the summary from after I've converted treatment as a factor. That's what you can see: the minimum, the first quartile, the median, the mean, the third quartile, and the maximum. And then more emphasis on the descriptive statistics. I did run this code here, and you can see that. I also ran a box plot. I don't know, can you see it?
Can you zoom in the box plot?
Okay.
Oh no.
Oh no,
Okay, that's okay. You can now talk about the box plot. It's okay, you can use that part.
Okay, fine. Now, from the box plot, I will not talk too much because I think Prof yesterday explained to us everything about it. So I just did this as a show of more of descriptive emphasis of the statistics I was making.
Okay.
And also I used the ggplot, and in the ggplot I created two different code script. That's the gg seed statistics, then the treatment and germination. This first code here, this one that I've highlighted here, when you run it, it only displays to you a table, but does not show you the more graphics. So that's why there's an importance of this addition of this code here, this script here, the geo box plot. So when you run this, that's why you can see this one. Can you see it?
Yes.
All right. Now, after having done that, I moved to find out the variation, and I did as I was assessing the effect of seed treatment on germination using the feeding linear model, and my analogy was that there was no difference in seed germination for the treatment methods, and so I ran this script here. And then for the ANOVA, it's here, and then you see what. So this is the results of the ANOVA that I ran. Yeah. And then moving onwards, the p-value is less than 0.05. Therefore, I choose to run the pairwise multiple comparison. And is that the p-value is 0.001787, which is less than the default significant value. So moving forward from here, running the least significant difference between the treatment method is where I couldn't. I've tried to maneuver around, but I haven't managed. So I think I will allow another person who did that. And if there's any addition of what I've said, I will appreciate. Thanks, Prof.
Thank you very much. That was an excellent attempt. Can we have another person?
Ashenafi. Let's say we have Ilyas, Yusuf, and Ashenafi, but
Let's have
Ashenafi's
Ashenafi.
network. Ashenafi's network is not stable. He has even gone off.
Okay.
But because Yusuf again presented yesterday, that's why I was suggesting I think we go with another person. And now I want to promote also by Gin. Ashenaf has come back, and also by Gin or by Gin. Brukataeti.
So we'll have one more.
Yes,
Let's have
there
one
is.
more.
But is it Bayelin or Bayelin? You can go ahead. Bruktaet Bayelin. Please go ahead. Unmute yourself and share your screen.
What is happening?
I think the participant is not unmuting himself. So maybe we go ahead and allow Yusuf.
Yeah, let's allow Yusuf to present. Participants, we've already sent you materials for today. We sent them in the morning. So you should be able to receive them if you registered.
So Yusuf, you can go ahead.
Good
I
morning.
see Shenafi is also coming back, but let's go with Yusuf.
Okay.
Good morning, everyone.
Good morning. Can you zoom in, please?
Yeah, so a minute. Okay. So as the question was posed, I entered it into R, and so I set my working directory and then loaded these libraries. So the first question was about the descriptive statistics. So I used the sorry. So I entered the data into Excel with the CSV extension. So my data is seed treatment in the working directory. So I imported it here using the read CSV. So in this project I'm doing, I decided to name it seed gem. So I viewed, let me run. Sorry about that. I want to run the, yeah. So with my data structure like this, let's view it in the tabular form. So the first column was treatment, the seed treatment, and the second column is the number of germinates. Now, my data structure, for now, the default is viewing my data, I mean the treatment as a character, and then my germinates as numerical. So I would have to change these characters as a factor. Treatment is a factor. So I set treatment as a factor in this R line. So let me run that and then check whether what certain treatment as a factor has worked. So I check the classification, and yes, indeed, R is now reading my treatment as factor. So my summary statistics shows on your screen. The minimum, these are the statistics. The median is 55.10, 0.10. Mean is 54.49. So I use the graphical descriptive method or approach, the box plots. So with this library already loaded in the general one here, I went ahead to run my project, this seed gem, and then I got this. So to view it in plots, I ran this code. So my germinates are the variables, and then my factor is the treatment. So the data is in this project, and I labeled my x axis, or my x axis as seed treatment, and then the y as the number of germinates. So yeah, I got this upon running. So you can see my axes are neatly labeled. And so with this box plot, like the previous presenter said, I would move away from explaining, since yesterday it was covered in depth. So we have 4 treatments here. And then I tried my hands on the ggplot and see how it would also show up. So with the ggplot, I set my project, the CGEM, such that my x-axis had the factor, which is the treatment, and my y-axis had the germinate, the number of seeds that germinated as my y. So I got this, which is, but for this one, and because I had already indicated these ones, it picked the default, what I keyed in as the germinates, the y-axis and the x-axis. So you can see this is slightly different from the previous one. So the next question was about the experimental design, which I thought it would be a randomized design, CRD, completely randomized design. And then, so I used a one-way ANOVA to answer the third question. But then there was something that crossed my mind here. I realized that the data structure was unbalanced. If you look at the number of the A's are 5 in number, 5 entries. So the sample size were not the same. A's were 5, then treatment B was 4, C was 4, and D was 3. But then I'll leave that for Professor Susan and Dr. Helen to help us here today. But then my entry on the analysis of variance on the one way, since it was just one factor, the treatment factor was 1. So I ran this code using the AOV function. So treatment was, as I called the germinate, the number of seeds in treatment from this project I'm working on. And so I got the summary. So this is the ANOVA output, where my p-value is less than the alpha level stated. So here it can be therefore be said that I had set my hypothesis in this line. My hypothesis was that the 4 seed treatments had the same effect on germination. And so upon running this, there is enough evidence to reject that the treatment effects are different, significantly different. And at this value, it is stated that it is different at this P level. It's even less than the 0.5 level. Now it is 1%. It's even less than 1% level. So the next was to do to test all the pairs of means, whether they are which treatment was different from the other. That is the pairwise multiple comparison. So with the LSD, I set my treatment as treatment, and then I ran. I got this output, which indicated that the treatment A and B are the same, just as treatment C and D. And so
Yusuf,
therefore,
increase the volume. Increase your volume. Speak louder.
okay. So I had set my LSD and got this output. This output indicated that the treatment A and B are the same. Just likewise, C and D are also the same. And so we can say that the treatments in A and B are significantly, if you look at the mean values, they are significantly, both are significantly higher than the treatments in C and D. Yeah, so thank you very much.
Thank you very much, Yusuf. I commend you, all of you who are presenting the exercises. That was a very good attempt, and I think it answers the question that your former presenter asked. He said he had failed to get the pairwise multiple comparison tests. And also, the CRD is robust enough to handle unequal replication. It is a problem when unequal replication occurs in a randomized block design. That is when we need to go in for, when we are analyzing data. If we, for example, if you conduct your experiment with the equal replicate for all treatments, but probably there is a flood and maybe part of your experiment is flooded, and then you collect the data from the remaining part, you will end up with incomplete block design. So there is an analysis for incomplete block design. But in this case, the CRD can handle unequal replicate. And also when you come to LSD, it will recognize that not all treatments have equal replicate, and the comparisons will be made according to the number of replicates. So for LSD, when the number of replicates are not equal, even the LSD values for each comparison differs. For example, A and B has 4 replicates, A has 5. Then when you come to B and C have the same number of replicates. So the LSD values will be different, but the interpretation also doesn't really change a lot, because when you're making comparisons between A and B, for the R package to assign those letters A, small b, they compare the difference between the two means and the LSD value. Okay, thank you so much. I think without wasting time, let's go to finish what we had not finished, the contrast, so that we also look at two and over briefly, and then I allow Dr. Helen to come in with regression, so that whatever is left will be completed on Saturday. Okay. The other thing is, I advise you to be applying. So if you see that your data is similar to the designs that we are talking about, or you also, for example, if you, or you have a question? Yusuf? Yusuf, you have a question?
Just a second, Prof.
Yes. Oh, okay. Thank you. So what I was saying, that if you see any analysis that suits your project work, just put a note and start practicing with your work, so that you can, the next day, if you have questions, you can come in the support session and you ask those questions concerning your project. Okay. Okay, so let me share the R script.
Yeah. Yeah, so I will share the. Hello.
Hello, yes.
Can you hear me,
Go
please?
ahead.
Yeah, there is something I wanted to quickly touch on it. In the LSD, when I wanted to present it in graphical formats, I
Yes.
realized that the script I had, this place had 040. So I figured out that that was the axis, the y-axis, the length of the bars.
Yes.
So I had to look at the mean values and then use the maximum mean value to set the length of the bar. So I just
That's
wanted
correct.
to clarify that.
Yeah, that is correct.
Okay.
That's what we do. Okay, and that is good. Thanks for raising that to the participants. Okay.
Thank you.
You're welcome. Okay. Yusuf is good. Huh? Okay. Okay, let's go to R, ANOVA. Everybody should have that script so that I want to zoom in so that it's a bit visible. Okay, is that fine? Okay, so you know that when you're going to run an analysis in R, the first thing you do is to set your working directorate, and that's what I'm going to do. So I will set my working directorate to where my data files are, and that is follow-up. Okay, then I click open, and I have some red. Let me just clear it. Then I go back, session, set working directorate, choose follow-up, and open. Okay, then I load. I'll load my packages. Okay. Afterwards, I'm going to go right straight to where we ended. Remember, we had done an analysis of variance. And before I go there, I need to read in the data. So I'm going to read in the data we are going to use using the CSV read command. So there we are. And then I make sure I change it to a factor. Those ones I'm not showing you because we've already done them. Okay. So then I am going to go to contrast. Okay, so we had already looked at that. I'm going to the pre-planned contrast, but I wanted to write something on the whiteboard before we go to so that you can understand how I got these coefficients. Because when I was explaining, it appeared that people had not understood how I got the coefficients. So I will briefly shift to the board. Then also stop sharing a bit. And I am at the board, and I want to show you how I got the coefficients. So what happens that we have 4 species. So I'm going to write species. Is it clear now? So I'm going to write species here. Then I'll write the comparisons. Remember I said that A and C are exotic, so I'm going to put exotic here. Then I'll put indigenous here. Then I'll put exotic and indigenous. Those are the comparisons that we are going to do. So we have A, B, C, and D. Now, we are going to compare the exotic species among them. We want to find out is the effect of species on growth of the trees. Does it depend on them being exotic? So A and C are exotic. Now, when you are assigning coefficients, you make sure that when you are assigning coefficients, you make sure that you assign coefficients to those treatments you're interested in. The rest you assign them 0. So we are interested in A, so we are going to call A 1, and B will call 0, and C will call it -1, and D 0. Now, why positive and minus? Because you want to compare the mean of A and the mean of B. Normally we put A minus B minus C. So that's why we have +1 and -1 for the coefficient of that comparison. Then when we go to the next comparison, we want to look at the indigenous species. Does growth depend on the species being indigenous? Are there differences between the indigenous species? So B and D are indigenous. So we are not concerned with A, we put a 0, and we are concerned with B, we put -1, and a 0 here, and +1. So it does not matter where you put the positive and the negative. You can put it anywhere, so long as you're going to compare. Okay, then the last one, we want to look at the average of the exotics A and C versus the average of the indigenous. So we are going to put, so when we are looking at the average, it is the same as having A plus C over 2. That is our average. Okay, so we are going to award a minus here. Okay, then a positive here, then a minus here, and a positive. Okay, so you make sure that once you have allocated your coefficients to the treatments, you make sure that if you want to have orthogonal contrast, orthogonal means independent, they have independent information. The coefficients have to add up to 0. So you must make sure, check, if the coefficients add up 0, +1 plus -1 gives us 0, and then -1 plus +1 gives us 0, then also here we get 0. So that's the first check to find out whether the contrasts are orthogonal. Then the other check is you can cross multiply. We can multiply this first contrast, so I'll call this contrast 1 and contrast 2. We multiply them and then add up. If it adds also to 0, then the contrasts are orthogonal, or we can actually multiply all through. So if we multiply +1 times 0 minus this is 0. If we go here, we get 0, also 0 and 0, so we add up and we get a 0. So that is also the other way of checking whether you have independent or orthogonal contrast. Why do we want orthogonal contrast? Is to make sure we don't have the problem of family-wise rate that we had with the turkey test, the LSD, and the last one. B is wrong, is supposed to be a half. Okay, let me see B. Yes, B is a half. And then C is negative. And okay, so this is B is positive. Sorry, this should be negative. And then if this is positive, then this is negative. Because what we are doing is comparing A plus C, then we do B and D. So if I can write it here, we are doing A plus B over 2 minus, oh, okay. So I'm going to change the whiteboard paper right here. Okay, so we are trying to say that exotic is A minus C over A minus C, that is the comparison. Indigenous is going to be B minus D. Then exotic versus indigenous, we are going to have A plus B over 2 minus B plus D over 2. So we'll have those comparisons, okay? Then, how do we get these comparisons? Remember, we had 4 treatments. We had A, B, C, and D. So the number of orthogonal contrasts is equal to K minus 1 is the number of orthogonal contrasts. So here K represents the number of levels for the treatments. Since there are 4, we'll have 4 minus 1 gives us 3 contrasts. So when you're planning your contrasts during your proposal time, you should use this formula to get the number of contrasts, then check out whether they are independent. So let's go back and do the practical. Let's go to R and do the practical. Then we are going to interpret those contrasts. Remember that we set 3 questions. One of the questions is that, does growth depend on the species being exotic? Does growth depend on the species being indigenous? And can we compare the average of the 2 species? Okay, so we have them, the same coefficients I've set up are the same ones I've put here. And in order for us to fit contrasts, we need to run this package. If you don't have it on your computer, install the package called gmodos. And then you load the package. So I've already installed that package. You just have to put your cursor here and run install.packages gmodos. So once you've run that, then you run the library. After that, then you're going to run the first contrast. So I'm assuming we are all together at the same time so that we can run the first contrast. So what is it doing? It takes the mean of A minus the mean of C, but it is going to calculate the sums of squares for the difference and divide by the mean square error from the analysis of variance table. It is not like the way we do our t-test. And the other check for you to find out whether you have orthogonal contrast, when you actually calculate the sums of squares for the first contrast, the second contrast, the third, and add them up, they should add up to the treatment sums of squares. So that is just to check that whatever you're doing is right. So let me just go enlarge this window and we look at the output. So the output is actually telling us that you're comparing 0.5 minus 0.5, all that. These are the coefficients we put in, and the estimate, the contrast estimate is minus 13.6591. This shows us that we are comparing AC minus BD. It is telling us that the average growth for the exotic is less than the average growth for the indigenous species because we have a negative sign. And remember, we are looking at A, C minus B and D. Okay? And then we go and look at the p-value. You can see because it is a little bit wider, the p-value is right here. And the p-value shows that it's smaller than 0.05. So that particular difference, there is a difference in the average growth rate between the exotic and the indigenous species. And in this case, the indigenous species are performing better than the exotic species. Okay, so we got to run the next. Let's run the next one, which is the comparison between the two exotic species. So the coefficients, we've put them in, and we just run this. Remember, for you to run this particular part here where I put species, it is the model for ANOVA, which you ran before. So it's the one you're putting in here, and you're specifying that you're testing species. Okay, so then we run, and let's run also indigenous and look at them together. We interpret at the same time. So let's go and look at the output. Don't mind about these reds. I think it's because I've reduced the sizes of the window. So it says that when we fit for exotic species A and C, the difference between A and C is 0.998. It is positive, indicating A has a higher growth rate than C, but that difference is non-significant. You can see the p-value is bigger than 0.05. So we have evidence to reject the null that these two treatments are not significantly different. Then when we look at indigenous, we are comparing B and D, and the difference is minus 7.5. Okay, so this difference is significant, indicating that the average growth rate for B is significantly higher, lower than D. No, it's significantly higher than D because B is the best. The average growth rate for, I think what they did is they did D minus B. That's why we have a negative. But we will look at the plots, and you see that B has the highest growth rate than D. So for us to interpret this p-value, which is less than 0.05, we say that the average growth rate of B is significantly higher than D. Okay? So why do we talk about independence? Why do we talk about independent orthogonal contrast? We want to have comparisons that do not share information. For example, the first contrast, we are looking at the average of exotic versus the average of indigenous. In the second comparison, we are looking at only exotic, nothing else. In the third one, we are looking at only indigenous. So you find that the three comparisons do not share any information. And when that happens, then you have orthogonal contrasts. Okay, so that's all about contrasts. And can I see in the chat? Please share the previous learning materials. We've already done that. Error in LSD. You are in LSD, my dear. We are doing fit contrast. I think either you are not here. Error in install packages. Gmodos. Oh, okay. Let me go back to that, but you must have written it wrongly. I can see the way you're presenting it here, Margaret. Okay, let me just briefly. Huh? Oh, okay. It says gmodo needs tools. When you see gmodo needs tools, you need to update both your RStudio and your R package. Okay, but if you've written your command correctly, that install.packages in bracket, inverted commas, gmodos, and doesn't run, then the problem is the version you have. So you should have a better version, okay? Says got the script but share the data. You still have, it's the same data called forest. It is the same data we are using. Object species not found. You didn't run the ANOVA. So make sure you run the ANOVA model. I didn't run it because it was still in the system. So if I can go back briefly and show you that you remember here, you see species here. I can go back again, right here. So you can see that I call this model, the ANOVA model, specie, which is equal to AOV growth, a function of species, data equals forestry. So this specie here is the one I'm using even in the contrast statement, okay? So if you've not run it, then you'll get a problem down here. So make sure you run that specie part of the model. So let me just run it. And why I am running it is because I want you guys to follow quickly. So if I go back here and run, and then I say run, so I get my summary, I am going to be able to use them under LSD, under the Turkey test. I'll use them all through, plus even the plots. So apart from errors in R, I think you people, the contrasts are okay. So let me go to the assumptions. You remember we talked about some 3 assumptions: constant variance, independence of residuals, and normal probability plot. That means that the residuals should be normally distributed. So we have 2 options. You can use this plot in bracket the model. The object is the name of the model, ANOVA. And when you put your cursor right here, I hope everybody is here, and run, it says figure margins are too large. So what I'm going to do is to either do this or go back to view and zoom out. So I'm going to zoom out, and zoom out. So then I'm going to run it again so that I see whether it can work. So here we are, specie, run. Once you run plot in bracket specie, it says you go down in the consoler. If you go down in the consoler, you see hit return to see the next plot. So hit return, the next plot comes up. So let me zoom the plot. Stop sharing. So that is the plot I've drawn. So this is a plot for testing whether the residuals have constant variance. And if you want to find out whether residuals have constant variance, this plot, if it has just a random scatter of points without any systematic pattern, for example, maybe a sigmoid pattern or a funnel-shaped funnel, you know, like a funnel, you know how you do a V and turn it on the right, that is what we call a funnel. Then if that is not existing in the plot, then we have constant variance. Just like you see here, we have just a random scatter of points, And it is also showing us that our data is in groups of A, B, C, and D. Okay, so that is the plot for constant variance. I am going to stop sharing and share the R script. And it says hit to see the next one. Then we have a normal probability plot. Let me just show it from here. So we have this plot which is testing for normality of residuals. If the observations follow on the dotted blue line, then the data is normally distributed. If these dots deviate from the blue line, then the data is skewed and we can do something else. So then I hit enter again and it says something. Then we have the last one. There are 12 warnings, use them. Okay, these warnings are not really, it is saying that the hat values leverages are all 0.6 and there are no factor predictors on the plot number 5. So it couldn't construct the last plot because most of the leverages are 0.66. So before I draw the last plot where I'll have all of them at once, I want to clear this and go to the command. So I want us to construct all the rest in one go. So we use this command pow mfro c22. Then if we run that, okay, then we run specie. It's going to present 4 of them at a go. So I'm going to zoom this. So there we are. We have our 4 plots. We have the constant variance one, which I showed you initially. And I say that if we do not have a funnel shaped, then there is constant variance. Sometimes you see values forming a curve or a sigmoid curve, showing you that you need to pay attention to your response. Here it is just showing a random scatter of points in groups, and it indicates that we have 4 groups. Those are the species A, B, C, and D. So here we have constant variance, and here I've just said that the points fall on the blue line, indicating normality of the residuals. And also here we are looking at standardized residuals versus fitted values. Fitted values are also called predicted values, and we calculate them by getting the observed values minus the predicted values from the model. Okay, so here we've not gotten the plot for independence, but my colleague Helen is going to talk about it, so you will see it. Okay. Okay, so unless if you have a question, let me look at the chart. Scale location shows what? We see it is it has standardized residuals instead of residuals versus fitted value, also showing constant variance. Okay. Yes, somebody is showing, is it possible to compare 20 groups on site? It is, I think that one needs the gear and E analysis because there are so many observations. What if normality is not maintained? And what if, okay, let me close this and look at the Q&A also. I didn't get the materials, please share the materials. Then I can see somebody has, what is the meaning of the last line? The last line has 4 observations deleted due to missingness. You remember that our data was not balanced. So that's why the 4 missing observations were deleted. They were not included in the analysis. Okay. The other person says, box plot. This problem I encountered when I ran my box plot. Okay. Pardon?
Can you present pairwise comparisons graphically?
Yes. Okay. So for this error here in the Q&A, can you please copy it and paste it in the Word document, in Google, so that in case you don't get it, we can help you during the support session. What's the difference between residuals and scale? Residuals have just said that it is the difference between observed values and predicted values. Okay. Okay, there is a comment here about POW. Remove the other bracket. There is a bracket there which you need to remove on the word POW and it will run. Somebody had internet problems. Okay. Okay, so let me share the R script. Okay, so when you want to remove the graphs from the graphical or plot window, we use this command here, POW, but initially there was a bracket here, a closed bracket. So if you run it, it gives you an error. You can see it is already indicating red. So you delete that and run. It is going to remove the graphs. Or it's going to remove, actually it's going to remove this first command where you want to draw graphs 2 by 2. Okay, so one thing I wanted us to hint, I'm not going to go to the notes PowerPoint. I was given a few minutes and I've exceeded. Helen is about to eat me, but she has forgiven me. So we are going to look at 2 and over quickly, and then I leave Helen to come in because I want you also to benefit from Helen's work. That's regression. But you'll also be with her tomorrow, so she has forgiven me. So we have this data yield, and I'm going to read it in, so everybody should change to yield. Let me just zoom in so that the commands are a bit big. Okay, so that is fine. I think now everybody can see the commands. So what I did was to run that particular command and then run yield to show me the data in yield. Or if I don't want to see the data, all the data, I can say head in bracket yield and run so that I only see the first 6 values, 6 rows. So you can see that I've seen the first 6 rows, and the most important thing here is to see how block variety are written. Is it with capital letters or lowercase or uppercase, so that when you're writing your R script, it doesn't give you errors. Okay, then I'm going to go in. We need also to see the structure. So str is for structure of, which you can type in. So we see that variety is a character, block is an interval, and yield is numeric. So we have to convert all those. So we are going to say yield okay. Okay, so I was checking my commands whether they are right. I didn't want just to write anything, so I'll call it yield. So you can just include this, and then we call factor in bracket yield $, block. Then we go and type yield again, factor. I'm doing this for the benefit of those who are new to R. When you're new to R, you go slow, step by step, and want to change variety. Okay, then we can run this. Okay. Error in operation variety. Let me see variety. Okay, my spelling is wrong. Okay, factor. Okay, so we want to change yield to a factor, and we have yield. Variety, okay. Okay, let me check str yield and check whether my, it says I have factor levels. Why is it doing this? Let me just check on something. Yes. Sometimes, yeah, I have to do another. Yeah. No, just type your yield then block. Use as a factor. One take a more. Take a block. As a factor. Then compare. And the first time. Block as a factor. Okay. Now try to personally render. Now compare these two. Okay, sorry about that interlude. I was getting to find out why I was getting the red, the error So how did I sort the error? First of all, I have to introduce yield $ block. Then I use as factor yield $ block. Then yield $ variety as factor yield $ variety. Then when we run, we find that they are working instead of the other method. So you can see it is now has converted both block variety to factor. So when I come to fit my model, I have to put here yield $. Then also here yield. Okay. Okay, so let me try to run and see if it runs, then I don't need to include that part. So this is the ANOVA for randomized complete block design. Why do I use randomized complete block design? It has 2 factors, and then in this case, we need to use a 2-way ANOVA. Sometimes it can be a CRD, but with 2 factors. Then we also need to use a 2-way ANOVA. So when we run, we get our summary. So I want us to pay attention to the summary below here. So I'm going to highlight it. We are not concerned with the blocks. Their job is to control the background variation in the experimental site. We are concerned with the effect of variety on yield. Are there differences in variety as far as yield is concerned, or does yield vary per variety? So we are looking at the hypothesis that there is no difference in the average yield between the varieties. And then when we look at our analysis of variance table, we find that the p-value corresponding to variety is small, it is 3.19 to the power minus 5. It is smaller than 0.05. So we have evidence to reject the null and conclude there are differences. I told you that once you know that there are differences, then we go and do our pairwise comparisons. Okay? Once we know that there are differences in the analysis of variance, we want to know which particular variety is doing well compared to the other. So in that case, since we've already done this, maybe I just show you LSD, we've already done it, so you can do it during your free time. I just wanted to answer the question where people are saying that, can we put these means on the bar chart? So I'm going to run the LS and run. So the output for LS, just like yesterday, this one has subscripts. We say that means with the same letters are not different. Okay, so this you can go and try to interpret. What I want to do is to draw this bar dot group where I'm using the LSD values. So let me draw that, and it's saying the figures too small, the margins are too small, so I can do control minus or zoom in. Let me zoom in so that I zoom out so that I reduce the sizes of the windows. So when you get a red, you can see that they are coming back. So let me run it again, and so we can see that we have our plot. I'm going to zoom into the plot. Stop sharing. So there we are. This is our plot from the yield data. It is saying that variety E and D have no differences in their yield. You can see that even their bars, the means are almost the same. And they are also saying, you can see on variety F, we have a there. So variety F is also not significantly different from D and E because there is an A, but it is significantly different from C, variety C. So we said groups or varieties with the same letters are not different. Here on F we have two letters, A and B, meaning that wherever you see A and B, variety F is not different from those varieties. So it is not different from E, D, A, and B. Variety F is only different from C, variety C, because C has a letter C on it. Then when we come to A, variety A is not different from F because you can see there is a B, and also on F there is a B. And variety A is also not different from B, not also different from C, because the letters you can see B, C. Okay, so when we come to C, variety C is different from all the others except A and B. And which of these varieties have the highest yield? It is variety E and D. They have the highest yield. You can see this graph here. Our bars don't really start from the beginning line of 8, so we can actually adjust them using the minimum value. So you have to go into your data, look at the minimum value, and adjust the scale of data using Y limit. Okay? So unless if there is a question, let me go to the chat. If there is a question. Okay, somebody is saying that categorical variables need to be set as factors. Okay, thank you. Can contrast also analysis be an alternative to pairwise? Yes, contrast is the best analysis instead of pairwise, because contrast, especially orthogonal contrast, control the problem of family-wise rate, whereby the significance level keeps on becoming bigger and bigger. You're no longer working at 5%. So it can be an alternative and the best alternative. Okay. Okay, so I can see some people were advising on what to do, but I couldn't see them. So a new message. Okay, thank you very much. I have an error. You called it yield 1. You're supposed to put a $ block in front of yield, the object. So Godwin, put a $ in front of the yield object block, then you put equal to as factor yield a $ block. So it will work. Okay, so unless if you have a question, I think I'm going to request that I stop here. Yes, can you please reshare the materials? Please reshare the materials in the chat. How do we get means, standard errors? We can use the function ls means. LS means it gives us the standard errors, the means, and standard deviations. I have error in LSD test. Godwin, you need to, you still have an error? Okay, let me go back to the script and show you my script briefly. Time is running out. Only that, then we stop because I am eating on Helene's time. Okay, there we are. So this is the command that I've written. So you can write yield. Remember, yield is the one that you read in. So the object that you used here, on line 1112, the first one here, is the same object we are using here to first of all, to run our data. So you have yield, $ block, the less signs, and as a factor, then you put in yield $ block. Then you run, it's going to run, okay? Okay. So I think I'm going to end here. I'm going to give an opportunity to my colleague. I think the things which are left, if you run them, you'll get the same results. For example, bar.error, you'll get the graphs there. So you can practice, and in case you have a problem in the support session, we can always help you. But we look at factorial after Helen has talked about regression. So I promise to come back and be with you again, but I'll be with you in the background answering your questions. So I invite Helen, the floor is yours. Thank you. Thank you, participants. And thank you again to those people who presented the exercises. Okay, bye-bye.
You're muted. Okay, good afternoon, good morning, depending on where you are. It has been a great interaction with Professor Susan. Now let's proceed. And during the answering of the questions, I got a question that was so interesting. Somebody was asking that I'm requesting for the R software and the gmodos to be sent on my email. So I encourage everyone, we said earlier. Now, what came to my mind that this person is missing some information from the previous training. Maybe in case you go back and check in the previous videos that we had, you'll be able to know how you can get R on your computer and then install on it. So let me confirm. Can everyone hear me? Just type a yes. Okay, great. I just want to share my screen. Sorry? No. Okay, welcome to linear regression with R. We are going to briefly first go through a little bit in the theory. Of course, like most of the things have been discussed by Professor Susan, especially when it comes to hypothesis testing. So at this particular time, I guess at least everyone know when to reject and then what is supposed to consider, because it really stresses many students on when to reject and when fail to reject. And linear regression, it's a commonly used statistical test in most of the data, especially in survey data. Although, so it's a reason why we also need to understand how can we use and when should we use it. Okay. All right, so we are briefly going to go through simple linear regression, what it is, and then we get to know how a good model looks like. Just a brief hint, but what is most important right now, it's how do we do it in R, but sometimes it's also important to understand the theory bit, then you can quickly attach meaning to the results that you get. So like a simple linear regression, you hear the word simple. When it comes to regression, what should come to your mind is that you need both the explanatory variables, call them the independent variables, and you also need a dependent variable. So everything emanates from your objectives. How do you set your objective?
it will be the one to tell you which what is going to be your dependent outcome and what is going to be your exploratory variables. So with regression models, we want to predict which responses affect we want to predict how the outcome is affected given a set of predictor variables, or call them the independent variable. So with a simple one, most of the time we consider one independent variable, and then with the multiple regression, those two we are going to go into more details, we consider more than one variable. With a good model, it is always important to see that usually graphically when you plot a scatter plot, it shows you how whether your data has really been presented very well or it has been poorly represented. And when you plot a scatter plot, you're able to see the moment if data lies mostly on the line of best fit, then it implies that that the data has been well presented. But the moment it's far from the line of best fit, then there is a problem. You can tell that it's a bad fit for that particular data. Okay, so it's simple linear regression. Most of the time, if some of you remember how to write the equation of a line, that's where the whole process comes from, that my y is equal to mx plus c, whereby we used to say that my m is the slope and then my c is the intercept. So it's the same idea that we are trying to bring on board. So with a simple linear regression, if you're seeing where my cursor is, with this particular equation, I'm having y, which is my dependent variable, and the x is my independent variable, whereas epsilon is my error term. Maybe just to give you a brief of what we are going to do, we are still using our diamond data set. And it's quite interesting that every now and then, despite the fact that we are facilitators, but even as we keep learning from you as well, and also learn from Professor Susan, there's one thing that has really caught my attention in this training, that we need to attach meaning on the results that we get, such that people outside there can attach what exactly the data speaks. So in this particular case, we are using diamond data set. So we need to ensure that the results that we get, we attach meaning. When I was sending out the data set, I said that we are looking at the different factors that might affect the price of diamond, as we are going to see as we move ahead. So let's assume, like in a situation, we have a business person dealing in diamond, but there are within the market, there are various things that affect how diamond, maybe the market performs. For if you're dealing with diamond, the price comes in, the colors, the weight, and so on. So just have that at the back of your mind as we proceed. Okay, so the beta naught and beta 1, back to the slides, are the parameters, and that beta naught is the intercept, then beta 1 is the slope. So we need to find these particular parameters. Okay, sorry. I'm going to slow down. They're complaining that I'm going fast. So we need to, from our data, the data helps us to find what these parameters are, or what the regression coefficients are. My beta naught and beta 1 is what we call the regression coefficients. And they can always be gotten, their numerical values can always be gotten from the data that you have. Okay. Well, the popular methods within statistics on how you can compute these regression coefficients, so the parameters that we have. And the commonly used ones, we have the methods of least squares and then the maximum likelihood. Since we are about understanding data and attaching a theory, we aren't going to go into too much details of how these methods work. But I encourage you, in case you're interested, kindly, you can Google out and read how they really work out. Okay, so with the least square estimation, most of the time when you look at your data, you need to find out how the data looks like. You need to consider what is your X and then what is your Y. So within this particular bullet, for example, I've got XI and then YI. So these ones could act as my variables in the model, but this is just an example that I've put up here. And then, so you can, yes, for example, I'm having observations 1, 2, 1, 2, 3, 4. Then I've got Y and then X. I can call y as my outcome or my dependent variable, and then I can call y as my independent variable. Now, referring back to the data that I sent, the diamond data, which is saved in the lab 2 data set, we've got various facts. When you look at that data set, it has got different variables. The variables that we have include weight, quality, color, price, length, width, depth. But remember, we said that sometimes you can have data and you manipulate it depending on what you want to achieve. So you can collect, for example, like 2 variables, but you can manipulate those 2 variables into, for example, like 3 or 4, depending. So we'll always assume that whatever the observations that we have, they satisfy a simple regression model. So for the case of the least square estimation, we are still going further, but the point is that we want to minimize the sum of squares of the distance between the observed and the line the line. When you look at the figure that I'm portraying here, we have got the fitted line, which is y is equal to beta naught plus beta 1x. Remember what I said? We need to calculate our beta naught and then the beta 1 from the data. However, how this line, seeing this line of best fit, we've got other data, either that it's up or below the data points that you're seeing. So what the least square method does, it tries to minimize the distance between the variables on the fitted line or the predicted values and the observed one. So that's why we use the least square estimation. The point is that depending on any model that we are using, we need to minimize the errors as much as possible, because when the error is small, then it implies that even our model that we've developed will be the good one. So this length that you're seeing between the predicted line or the fitted value and then the observed value is what we call the residue. I know Professor Susan has talked about residues as we've been moving on when he was talking. So, or you can call it a modeling error, or you can simply call it an error. But what you want to see that it is as small as possible, because the moment it's big, then it will imply that our data has been poorly represented. Okay, when you're going to the mathematical bit, this is what you'll find. For those of you who are interested to Google more on how to get the coefficients using the ordinary least squares, but I'm not going to go into details of that. The same applies to this slide. If you want option B on how you can calculate the beta knots and then the intercept, among others. So it's always important to understand what a residue is, which you've just talked about. And then the fitted line, it's a line that really shows, it's a line of best fit that shows a great representation of our data. And then the residue, like I said, it shows the difference between the observed value and then the fitted value or the predicted value. So that's what a residue is. And so here, what we are trying to see is that the moment we determine the coefficients, the regression coefficients, then it implies that we are able to determine the predicted values. That's what you're seeing here, as we are going to see that. And I've already mentioned that for the residue, you get the observed value in this particular case, then minus the fitted or the predicted value. Okay. Also something more useful, because most of the time we talk about the residues. The point is that we need to minimize the error within our work. And so in that particular case, we've got some useful information we need to consider. For example, the error sum of squares, whereby we sum the different errors. For example, in case you see here, we get the observed yi, then minus the fitted values, and we square them. So in that particular case, we are able to get the error sum of squares. And we are going to see how these things are determined and how they are really important. There's also another component we need to understand about the coefficient of determination. Most of the time as we do regression analysis, we always see R squared, R adjusted. but we also need to attach meaning, and we get to understand what does it really do, or what is its relevancy when we're doing linear regression. Okay, I've just talked about the coefficient of determination. Usually, we've got a lot of data, and this data, most of the time with your outcome. For example, in this particular case, we talked about that price is our dependent variable, or our outcome that we want to see, how the other various factors that we have in the data affect price. So the R squared will tell us that how much of the variation has been explained by the different, how much of the variation has been explained by the dependent variables to tell us how price performs. So that is the R squared. It tells us the proportion of variation in the dependent variable, in this particular case, which is price, that has been able to be explained by the model, considering the other factors. Okay, yeah, that is just a pictorial of coefficient of determination. Now let's move on to multiple linear regression. When it comes to multiple linear regression, in this particular case, all what we do is we just add another variable. Remember, with a simple linear regression, we only considered one variable. But with multiple, you can add in more dependent variables. For example, if we had in the linear regression, the simple linear, if we had like price as a function of weight, as a simple linear regression plus an error, this time around, you can add as many dependent variables as you want. For example, in what I'm giving here, that you can have a response, which in this case, it's price that is equal to the baseline, my beta naught. You can add in other coefficients as much as you want. And the betas that we are having here, they show us, they are trying to give us the effect of the dependent variable. For example, either when you're increasing or you're reducing by 1 unit, what happens to the outcome or the dependent variable. Okay, yes, a lot has been talked about hypothesis testing, but one thing that we should note at the back of your mind is that the moment you set up a linear regression, we want to understand how the dependent variables are significantly related to the dependent variable. Are they significant or they are not? So the point of a hypothesis comes in, because by the end of the day, you need to come up with a conclusion of the many variables that you have. Which ones are you going to say, for example, within the data set that we have, that they do affect price? Of course, you can have very many, but when not all of them affect the outcome. With a hypothesis, when it comes to linear regression, most of the time we are going to look at our regression coefficients, the betas, because they are the ones that measure the strength on how the independent variables affect the dependent variable. So as we said earlier, within our hypothesis, we are going to set our betas to be equal to 0. And then the alternative, of course, it's the other way around. You can, depending if in case you know the direction, or in case you do not know, you'll have to use a two-sided type of hypothesis. We've got our t-test. We are going to see that we are also going to determine that. You can also, we have the critical value, and then also the confidence intervals. Theoretically, we're going to see, sometimes, you know, they'll tell us that looking at the estimates that we've got, maybe, I mean, the likelihood of where it's supposed to lie, giving us the upper, the lower, and then the upper boundary. Now, that is just a brief of what is happening. What we are going to do, we are going to move on to R, and then more responses. I'll explain them from there. Maybe it will make more sense. Maybe what we are going to note, what you have to note at the back of your mind, that you need the HMIC package stored, loaded in your package. We are going to use it, and then the LM function or the LM command. And inside the LM command, what we usually do, for those of you who have just joined, first when you open the LM command, on your left-hand side, we put our dependent variable, the variable that you want to test how it is being influenced by the independent variable. And then on the right-hand side, we put the independent variables, or the independent variable when it comes to simple linear regression. And also within the same function, we indicate our data. Data is equal to the data frame. But I guess at this particular moment, at least most of us know what a data frame is. Sometimes you can also assign your model. Maybe you can assign it an object. You can call it maybe model. You can call it anything that you want. So you can say model is equal to what your regression equation is all about. And then we also use the model summary such that we get detailed information on how the model has performed and then the coefficients, because by the end of the day, they are going to support us on how we can improve the results. Okay, now I'm going to go to R, then we see more explanations there, but I've already sent all this with you. You can take a quick look and read on some more details and see how things work out. So I'm going to stop sharing and then now move to R. There is a question that says, remind us what a data frame is. Actually, a data frame is just the data that you have. Data frame is just a language that is used in our programming language. For them, they define it like a spreadsheet. Where your data is, it's in a matrix form. Where we have got the independent variables listed on the top of the rows, and then we've got the top of the columns, and then we've got the observations on the rows. So what you see, the data that is being captured within an Excel, that's what we refer to as a data frame in a simple term. Okay, I'm going to share my R now, and then, all right, so everything of mine is clean. So let's try to see how we are going to do it. But remember the basics. Right now, at least everyone should be able to load the libraries. And then the next important thing is to import data into R. Because if you don't import it into R successfully, then what are you going to do? You won't be able to do the analysis. So now what I'm doing, I'm going to load my libraries, the libraries that I need for this part. So there. When I look in my console, it is showing me that the libraries have been successfully loaded. Let me ask in the chat, can you be able to see my R script? Okay, fine. Since you've said yes, then I don't need to zoom it out. I can move on the way it is. All right. Now, we are going to first consider, when you look in the scripts that we send to you, most of the time there are comments. Always take advantage to read them because they support you to tell you what exactly we are doing. Unless if you want, you can convert them into an R markdown. So the first thing is to set your working directory. We have various options on how you can import your data into R. But it's always good to consider what is simple for you. I might import it in a different way, and then there's also another easier method that I can use. So, use the one you feel it is easy for you. The point is getting data into R. So when I set my working directorate, for me, Prof does it in a direct way. And that is also simple, but you can also go to your folder and check where your data is, and then click that path from the top and come and paste it into R. Then that is also another option. We are using lab2 underscore data CSV. Let me ask in the chat, have you been able, open also your R Studio, and then we start working. Have you been able to import lab2 data? Okay, fine. Let's work together as we move on. One is saying not yet, so I kindly ask that now. Okay, somebody is saying that, can I demonstrate the path? Can you demonstrate the path checking method? I'm still installing the packages. Wow. All right. Somebody is saying that I demonstrate the path. Now let me stop sharing, but I'm only doing once. Kindly pay close attention because we want to move on as fast as we can, such that we really cover a lot. We get the knowledge on how we are going to analyze our personal data. Like Professor Susan advised that as we are working through this journal, understanding how to analyze data, and you've got your personal data set, in your free time, try to relate what you're learning to the data set that you have and see whether now it makes sense for you or not. Okay, I'm stopping to share. Now, for the other method, but like I said, you can use any that is simple for you. My work, I want to show you just briefly on my computer. This is the folder where I've got the the follow-up linear reg2.r script that I'm using. Okay, but still at the same time, I want to command R that, you know, the folder can be on anywhere on your computer. It doesn't matter. It can be in my documents. It can be anywhere. But the point is to get a path where that folder is. The moment you command R, that within this particular folder, that is where my data is, then the rest will be very simple for you. So what you do, you make sure that the folder where you're working from is open. So what you do, you come, hope you're seeing where I'm moving the cursor, you come and click there. The moment you click, you're going to see that there is you're seeing a blue something that is highlighted in blue. It varies from computer to computer, implying that what will happen on your computer will be different from the rest. It is unique. So what I do, I copy what I'm seeing up here in blue, because it's telling me that from my computer, the navigation on on my computer, what is the navigation to the folder that has got my data. So from the computer, you go to users, you move to the desktop, follow-up materials, and then to the folder where the data is. So what you can do, all you need to do is to just copy that. The moment you copy the path, that is enough that you need. You go back to R and then paste it there. And all you need to do is to change. Instead of backward slash, you put them to forward. So I'm going to stop sharing this. And then I share again my R Studio. Okay, now after copying that, what you do, like I said, you just come into your R and then you paste it. You paste that navigation you're being given. After pasting it, all you need to do is now to put the set W command and change the backward slash to forward. So what I do, I put set WD, okay? And then I put everything in bracket, the path. The next thing is I need to change now the backward to forward. Okay, I need to change everything from backward to forward. And after that, I put quotes in my path. And that is all. So it is what I was running here. The moment that path is right, R and you run it, R will see in the console that there are no errors. So let me ask in the chat whether you've been able to kindly import data into R and we proceed, the lab2 data set. If you're seeing the blue line, copy it and take it into R. Okay, then import your lab2 data set and you give it any object name and then we proceed. Okay, now when I move on, remember we've been talking about object or assigning your data the name that you want, but sometimes, Okay, somebody has an error in the chat. That no such, then it implies that you need to check the path again. Maybe there is a problem. And then also indicate double quotes, not single quote. Indicate double quotes at the start and then double quotes at the beginning. And you use set WT. So it is set working directory. But the point is, use any method that you feel is simple, because by the end of the day, you're going to do the same thing. All right, now I'm putting my data. It is being saved as lab2 data.csv. Remember, you can also have your data saved as XSLX in an Excel sheet. And there's also a way on how you can import such data. But most of the time, we are using the possible or the easiest options that most scientists use, such that they support us to quickly analyze our data. So I'm importing my data using the read.csv command, and I'm putting a name. I'm naming it diamond. Remember, this is our assignment. So when I run that, I look in my environment and they're telling me that this diamond data set that I imported has got 100 observations and 7 variables. We've been talking about head. Head tells you, sometimes it's always good to get familiar with the data that you have. And in this particular case, maybe you can take a look at the first 6 rows, such that you convince your brain that, yes, this is the data that I imported. So when you look in the console, I'm having the first 6 rows of the whole data that I have. Let me ask in the chat, can I proceed? Stop at the 4 minutes. Okay, fine. I increase it. Okay, fine. When is it? Okay, let's proceed. Now, remember, the best things that we always do when you're starting to analyze your data, to get familiar with your data. For example, now we've seen the first 6 rows. You can also check and see the structure, such that you're going to know the different level of measurements that are attached to your data. So if I type str and then I put diamond, okay, when I run that, when you look in my R console, I'm seeing that they're telling me it's a data frame with 100 observations and 7 variables. Then I've got, among the variables that I have, I've got weight, quality, color, price, length, width, and then depth. But remember, with quality and color, they look as character. So I need to tell R that please look at quality and color as categorical variables. So I convert them to categorical using as a factor command. Okay, so this is what I did. In my diamond data set, go get quality and then change it to categorical, then the same to color. So I can run those 2 lines. I guess we are good to go. We are all good there. Now, as we proceed, when it comes to linear regression, sometimes it's always good to check on how using a scatter plot and see how the data looks like, because what we're going to start with, we are looking at price as our dependent variable. The price of diamond, we are looking at a business person dealing in diamond, and now we want to, how can he really, maintain, be in the business and be more competitive, and in the sense that I can be able to run his business very well. Okay, this was the data was collected. Some of you have been asking about survey data. This is an example of survey data. You're having a business person who is dealing in diamonds, okay? But now we are looking at various factors that are affecting the diamonds. So what factors can we, what information or what recommendation can we give to this business person, depending on the variables that we have, because all the information comes from what we have. All right, so right now I'm going to start with, I'm looking at price as my dependent variable, and then the rest of other variables are independent, so they affect price. So this is just, I just want to look at a simple plot whereby I'm using the scatter dot smooth command. I've got my X, which is the weight. I'm going to start with weight, and then my Y variable is, which is the outcome, it is price. And then main, most of the time, it is the title, okay? You'll see that when you print out the figure, the title will have a price as a function of weight. And then also, when you use scatter dot smooth, then it implies that you're also going to be able to see a regression line as you plot. So in case I run this line, when you check on your right-hand side on the bottom box, the workspace, we are saying we are plotting within a scatter plot. We're having price versus weight. And when you zoom it out, for example, in case, has the what? Dennis, I'm seeing that you're having an error on how to read your data into R. Have you been able to sort it? The lab underscore data CSV, make sure you put it in double quotes. We talked about R being case sensitive, so we have to follow also the principles. Put it in double quotes, not a single quote. Okay, I'm saying biotech, let's all equal read CSV, that is very okay. The moment the path is correct, then automatically reading data in R should be easy. Dennis, I'm asking again in the chat, is it solved? Kindly respond such that I move on. Okay. Really? It is the same. The script I sent is the same. Okay, now let me share. Okay, I'm trying to share the scatter plot where we are having price versus a weight. So sometimes we've been looking about that it's important to do data visualization because you're able to quickly attach how the different variables behave. So from what we are seeing, yes, we are being given the line of best fit and it's moving in the positive direction. So you can quickly attach and say, okay, depending on what I'm seeing, it implies that as I increase the price, because there is a positive relationship, then it implies that also the weight does what? The weight also increases. So you can try and plot that out and see. With the smooth dots, with the scatter dot smooth, it is the one that helps us to see the line of best fit or the regression line that is fit into the model. However, there are other various ways on how you can do the plotting without that line there. And we looked at them already. Okay, I'll cancel that. And then I share again my R studio. Okay, let me ask in the chat. Are we on the same page? Okay. How do you add a line to the graph? I said it will come automatically with the scatter dot smooth. It comes automatically. Okay, though there are also methods whereby you can tell that, okay, plot for me a regression line, or you can also just say plot a weight as a function of price, only that using the plot command, and then for it will not bring the regression line. But the point is the results we get are always the same. Okay, now let's move on. I'll not go through the notes. You will take some good time to read through the comments such that they support you. Remember what we said when you're dealing with a linear regression. We use a command LM, okay, LM. I don't know whether you still remember the help command in R. Sometimes when it's complicated for you or when you don't really remember what exactly you're supposed to do with a certain command, you can use help. Help is an inbuilt, it's an inbuilt function within R that can support you, because the R has got various documents. So the moment you type help, maybe on LM, it will tell you, okay, that you need A, B, C, and D. These are the arguments you need, and this is how you're going to use them using the help command. So within my LM command, what I do, I'm going to, I'm plotting price, the outcome, my Y, okay, that I'm fitting, and then weight as a function of weight. It's simple. With a simple linear regression, we consider only one variable. So what I'm going to do, this is the line that I want to run. I've called this is the model. Price is a function of weight. I'm considering the data as diamond, okay? And I've labeled it model. Remember, you can give it any name. It doesn't matter. So in case I run this one and I run it there, so now it's in the R console, it tells me that the results are okay. Okay, the model is fine. So in case I run its summary, let's check what do we get. In case you run the summary and you come down here in the R console, there are different results that you get. Okay, first of all, if we look through all the interpretation that we are having here, the point is you need to understand the concept behind, such that at the end of the day, the moment, like for example, if we end the lecture like this, then you are in position to apply the same knowledge to your personal data. That is the instance. So now, when I check for the summary of the model, this is the output that I get. First, it prints for me the formula that I used, okay, the LM command. That are within the formula, I printed price as a function of weight, and I used data diamond. All right. So after that, it brought me the residues. We talked about the residues, and it's always good, the good residues when they are close to zero, because we are trying to see how these residues differ from the line of best fit. Okay, so how in that particular case from the printing, they are giving us the minimum, actually the summary statistics of the residues. We've been looking at summary. We are having the minimum, the first quarter, the medium, the third, and then the maximum. Now, what is important when you're coming to the coefficients, okay? Like we said earlier, we've got the estimates. My beta naught, always our beta naught, it's the intercept. And this particular case, my intercept, the value that the data has been able to give me, it is minus 2112.3 with the standard error of 318.4, the t-value of minus 6.634. Remember our t-value, it's what has been calculated from the data. We've also gotten the p-values. And then the other one, the other variable, we put weight, which is 7456.8. With the data, R has been able to calculate for us the standard error. It has calculated for us the t-value, and then we're also having a p-value for weight to be less than 210 to the power minus 16. And we're having the 3 stars on the side. I don't know whether you still remember their relevancy. So what interpretation can you attach here? Because it won't make any sense unless you attach a meaning. Remember, we say that our weight is a continuous variable, right? So in this particular case, we are looking at the estimate, because the estimate, it tells us the strength of a particular variable that you're considering. So when you look at the 47456, in case you're looking at how the regression equation looks like. So let me ask in the chat before I proceed, who can give me an explanation of that particular value? Just type in the chat. Give me the explanation of the value. Type in the chat what risk. How are we going to explain the estimate for weight? Type in the chat. I'm waiting for the answer, then I'll consider that. Do you know what it implies? Anyone who just type the answer in the chat. Okay, Gashammer said, a weight increase in 1 unit, as weight increases by 1 unit, price will also increase by 1 unit. Again, really? Okay, Emmanuel says a 1 increase, weight will increase by the factor, the gradient of the line. An increase in 1 unit of weight will increase the price by that. The expected price is that for yes. Thank you. All the interpretations that you've put in the chart are correct. The point is that remember the estimate, it's our regression coefficient, the beta naught. So it implies that in case weight increases by 1 unit, here it is positive. That's why we are saying that it will increase. So it implies that when you increase weight by 1 unit, then it implies that price will increase by this degree, or the strength of 7456.8. All right. And and then we move on to again to check. When you look at our p-value, we want to check with the hypothesis that we say that with my hypothesis that my weight, or the coefficient beta 1 for weight is equal to 0. And you know, when we talked about the null hypothesis, we say that it's a probability of the probability for null hypothesis, and it is set as alpha when it's equal to 0.05. So this we want to check in case we want to make conclusion. What conclusion can we come up with? Given that the value that we are having here, it is less than 0.05, so we can statistically be confident and conclude that we reject the null hypothesis. In this particular case, we reject the null hypothesis, and then we conclude that there is significant evidence to show that weight affects price. All right. And now when you move on, also the other important thing that you have to note at the back of your mind, somebody is asking that if weight is 0, how it becomes the price negative. All right, thank you. Within the chat, somebody is asking, what about when the weight is equal to 0? So in that particular case, in case weight is equal to 0, it implies that my y, or the price, will be equal to minus 2112.3. But when you look at it sincerely, does it make sense? Can we have a negative price? So in this particular case, when weight is equal to 0, it doesn't give any sense. So we can ignore that and only interpret what is most important, or what makes our results better, that they can really show the meaning. All right. We have to understand, even the signs support us whether there is a negative relationship or not. And then with the weight, it's positive. So in this particular case, the positive just shows us there's a positive relationship between weight and price. So it's also is important to note in case they are negatives, and then they support you as you're explaining. All right. Now, when you move on, down again on the results, we are having the multiple R squared, that is our R squared. We said how the data has been, how price, okay, the price variable, our dependent variable, has been explained by the data. The variation of how the variation in the data has been able to explain our dependent variable. And we are seeing that it is 0.8549. When you look at R squared, it's always important that when the value is close to 1, then that is a good fit. Whereas when the value is close to 0, then that will give us a bad fit. So now we are having 0.8549, which is close to 1. You can call it 85% of the variability in the data has been explained by price. Okay, and then now when it is simple linear regression, when it is adjusted R squared, most of the time the results are the same. Why? In case we move on to multiple linear regression, it will always be good that we always consider the adjusted R squared, because for it will not be inflated. Yet for the case of the multiple R squared, it is inflated as you keep adding in more variables. Okay, so that is somebody's asking, may you relate again? Sometimes the P is less than 0.5, but it's very small. with the p less than 0.05, like we said earlier, that maybe in that particular case, when the R is very small, it could be that you might be, to cope up with that, the data set might be very small and you need to collect more data such that you are able to add more variables in your data set, and that error or the possibility of having a small R squared is sorted out. Okay, let me proceed. And then we are having the overall p-value for this particular model, which is also less than 0.05. We already talked about that. So we reject the null hypothesis and say that there is a relationship between weight and price. So in that particular case, our beta 1, the bit of weight, is not equal to 0. Can I ask in the chat, can I proceed? Is that okay? Why is adjusted R squared less than the multiple R squared? In this particular case, as we move on most of the time, you're going to see that actually this, for the multiple R squared, which is 0.85, and then in with the adjusted R squared is 0.85. Most of the time when you look at the multiple and then the adjusted, the point, what you need to note at the back of your mind is that as we keep adding more values, you find that the multiple R squared will keep changing. Yet, whereas with the adjusted R squared, it ensures that it doesn't inflate the model. So in that particular case, when you're reporting for a simple linear regression, you can report the multiple R squared. But when we move on to multiple linear regression, it is always good that you report the adjusted R squared, because for it, the moment as you add in more variables within the model, the variables are not inflated. Okay, now the other thing that you can do, I'm proceeding, hope that is okay, is the overall p-value show the significance of the model? Yes, because in this particular case, what we are seeing that it's less than 0.05. So we are confident, and we can say that since our p-value is less than 0.05, statistically, we are confident that there is a relationship between our variables, in this particular case, weight and price. Does the value of the t value matter? Yes, most of the time, the moment the variable is significant, it's always most important that our t value is high. Okay, now we can plot our model and see how it behaves. So in that particular case, what we do, you can use the plot command, plot model. So from there, you can, I'm moving on to the next line. When you click a plot, you move to the console for you to be able to see the different figures. You move to the console. I hope you're seeing hit return to see the next plot. So what we do, you click enter. When you click enter, you find that within on your right-hand side at the bottom on the plot, in the plot box, you're seeing the plot that we are having. You can zoom it out. And then let me stop sharing and I share the plot. The first plot that we are having, let me ask in the chat, are you seeing the figure that are plotted? Are you seeing the figure which has got, okay, fine, great. Okay, now, in this particular case, we are seeing we've plotted our model whereby we are having price against, which was a price as a function of weight. And our main aim, if you remember very well, we said that we need to minimize the errors within our data. And here we are plotting the residues versus the fitted values. Okay, so we have got the residues versus the fitted values. And it's one of the reasons as to why we need to check and see whether our data has been properly plotted. But what you have to note at the back of your mind that while we are plotting, also we have to note that are the different assumptions meant. But the way, as you're seeing this particular data, as you're moving from the left and you're heading to the right, you see that when data comes, when it reaches somewhere like here, some of the data goes up and then some of the data goes down. And yet the main assumption we need to check is that the variance of the residue has to be constant. So we need to, in case the residues are not constant, what do? Remember, there is an option of doing transformation. So you transform your data and then plot down again. But in this particular case, let's move on and see other plots. Okay, I'm sharing my R studio again. Still, when you look in the R console, they are still telling you that hit to see the next plot. Let me ask in the chat, have you been able to see that when you have you been able to see the hit return to see the next plot? Okay. Most people are saying yes. There's a question that what is the difference between LM and then the GLM? With the LM, most of LM is, we do use the LM when those are linear models. Like the word you see, GLM, those are generalized linear models. For example, with the general linear models, the models that you can consider, they include like the logistic regression. So that's when we are going to consider those ones. And the assumptions and the definitions are totally different. So in this particular case, we cannot use the GLM. We can only use the LM, the linear models, because depending on your data, for example, with the linear regression, okay, most of the time you will see that one of the characteristics is that your dependent variable is supposed to be continuous in nature. And this particular case, weight is a continuous variable. Whereas when you move on to the generalized linear models, for example, like in case we are to consider logistic regression, I'm hoping that time will allow, and then we also we have a look at it, whereby the dependent variable or the outcome variable has got two outputs, or their binary outputs, for example, yes or no, or you can have even more than that in case maybe you move on to ordinal logistic regression or multinomial. In that particular case, you'll be using the generalized linear models, because you have to consider the family that they are coming from. Like for the logistic, whereby for it comes from a binomial family, the yes or no or false and true and so on. Does the negative value indicate? The negative value does not indicate the significance. All what it does, it just supports us to see the direction, whether there is an increase or a decrease. But what shows us the significance is our hypothesis that we put across, the p-value, where in case you test that it is less than or greater than, that's when the p-value is one that will give us the confidence to say that we are statistically confident that there is a relationship. But with the minus, it just supports us to see the direction or the strength of the coefficient we are dealing with. More questions are being answered in the chat by Professor Susan. Let's move. Now, when I hit again, now it is giving me the plot for normality, okay? The normal probability plot. Let me zoom it out and then I share with you. Okay, I'm going to stop sharing and then I show you the normality plot. Okay, now from what you are seeing, remember with the normality plot, the point is that most of your data has to move along this particular line that you're seeing. But we are saying that some of the data points move far away from this particular line there on the one that shows the normality. So most of the time in this particular case, that assumption is violated. For us to handle this, we need to transform the dependent variable, okay, using a log log transformation. So I'll stop that and then share again my RStudio. But as we are working, also try to hit and see that you see all these particular plots, because also you saw them during the experimental, when Prof was talking about the experimental design. The same thing, we are having another plot. If you're seeing it on what we are having the standard residues versus the fitted values. So you can also hit again, and you also see we are having the standard residues versus the revelage. Like most of the explanation, what was explained before we get into this lecture, the same applies. So sometimes you might want all these graphs to appear once. So what you do in R, you create a grid in the sense that you use a command PAL, then inside you put MFR row, which is, then in C you put 2,2. Remember, this is on my first row put 2 graphs, and then on the second column put 2 graphs. So in case I hit that, what it does, and then I plot again, it will bring me all the plots together on one plot. I'm going to just quickly share this and then proceed, because right now I guess you've gotten a feeling of how we do that. And I'm being told I've got 13 minutes, Prof. Okay, so these are the different plots that we have been getting, but the explanation is the same, whereby we are having the residual normality. We've got, the residual plot, then the normality probability plot, and then the one with the standardized residuals versus the fitted values. Okay, let's proceed. I'm going to try to move a little bit fast, and then we continue, such that we cover something. The next command you're having, it will still bring you the same thing, only that this time around, in case you want to see only the residues, this command here will only give you the first plot, because it's what you need to come and plot it in the second one. I'm going to leave that because it is the same thing that is being captured in the first one. Also, you can use the AOV in case you're using a simple linear regression. You can also use an AOV, that is analysis of variancy, and the results are going to be the same. So I'm leaving this particular bit, you run out that line and check if the results are the same, and they'll give you similar explanation. All right, now I was talking about that when we plotted the residues, we saw that some of the assumptions of simple linear regressions are being violated. For example, in the plot of residues versus the fitted value, we saw that our residues are not constant. We are not having a constant variancy. So what we can do is to take a log transformation of our dependent variable, and then we plot again. The moment we take a log transformation, then it implies that when we plot again, we expect to see no pattern this time around within our particular data, whereby we'll only be seeing normal on the normal probability plot that our data points are on the normal line. Okay, and this is what I did. I took a log transformation of price. That's why you're seeing the LOG, and then still as a function of price. So in that particular case, now I plot again, and then I get my summary. Most of the time, when you log transform, it's like you want to reduce the noise within the data set that you're having. And so the results that we are getting this time around, they are log transformed. And when we go back, when you're explaining the results, we have to unlog them again by using exponential unlog, such that you explain them very well, clearly. And in this particular case, I mean, the results are the same. The way we are going to explain is the same thing like I talked about it earlier. But I would just want to show you the fit when we log transform, what happens this time around. So I'm still asking R to give me a 2x2 plot. and then I plot the one that I've transformed. I'm going to zoom out, and then now this time around, show you what happens. So if I stop, I want to share now this plot. So what we are seeing that with the normal probability plot now, all the data points are concentrated on that line that I sent there. So it's one of the assumptions that we have to prove that, okay, right now our data is normally distributed. And then on the residue versus the fitted values, we are seeing that this time around, we do not see any pattern that is involved there. So we can conclude that our residues have got constant variance. So I'm going to close here and then go back to my R. And in case there are questions, I'll be happy to attend to them. Are we on the same page? Are we on the same page? Kindly type yes. Okay, wonderful. So I'm seeing many yeses. There's some code that I'm going to skip so you can, run them and see what they do by the same explanation. Now I want to briefly, in case you want to get the confidence interval, okay, for the model that you have, in R, you can use the conf int and then in bracket you put your model. Or in case you want to have a specific variable, for example, in this case, it's only weight. What you can do, you go into the conf command, type the model, and tell it that only give me the confidence interval for weight. And then when you run that, when you check in your console, it will show you your confidence interval at 0.95. That is at 95% confidence interval. You can as well ask at different levels of confidence interval, for example, at 9% or 90%. Okay, remember what Prof was explaining about the confidence interval. It gives us the likelihood where the estimate, okay, of weight falls. So outside that, then it implies that our weight coefficient will not apply, or to give us a bad fit. So in case you want to go back to a 1-by-1 or to the normal plot, all you need to do is, if you want to do away with the graphs, you can say graph off, they will all disappear. You won't see them again. And then I'm also telling R that, you know what, give me back, take me back to my normal grid of 1-by-1. Now, lastly, given the time that I have, I'm going to move on to multiple linear regression. I thought I'll cover model building, but I think it's a part that I'll start on that part tomorrow, because sometimes the question is, yes, I've gotten all these linear models. I've got the simple, I've got the multiple, but among all the many models that can come out of the data set, which one is the most appropriate, or which one that really, that I can say it's appropriate on the data that I have. Okay, now when we move on, with the multiple linear regression, this time around what we do, you add in more variables. Remember now, instead of weight, what I'm going to consider, you can add all the variables, or you can keep adding a little few. In this particular case, I added weight, length, width, and then depth. However, let me move down. When you look at this one here, there's model 3. It has whatever is in model 2. I said price as a function dot. The moment you put dot, it implies that consider all the variables. So instead of selecting a few, because sometimes you can be working and you have many variables, and you don't want to pick one at a go. So the moment you put price as a function of dot, it implies that it's going to pick all the variables other than the dependent variable. So let's run this, because the model 2, with the variables you're having model 2, let's consider them all at a go in model 3. So when I run that, okay, so I come and see the summary of my model. So still, what is most important is that we need to make an interpretation. Initially, with the simple linear regression, we only considered weight. But sometimes when you move on to multiple linear regression, you still want to check, did the variable I considered at simple, maybe when it was only one, is it still significant even if I include other variables within my model? Because sometimes you might find that as you increase the variables in the model, the one that looked significant earlier might be insignificant now. So now in this particular case, let's still walk through the explanation and get to know what how can you interpret the results, and then we see with which variables can we advise the diamond dealer to consider such that he can be able to compete in the market favorably. Still R prints for me the LM, the formula that I use, and it also gives me the summary statistics of the residues. The smaller R residues, the beta, because all what we want to do is to reduce the errors that we have in our data. Now, as you move on, when you look at the coefficients, all right, remember, now in this particular case, we've considered all the variables, and you have to note at the back of your mind is that some of the variables this time around, some of them were categorical, others were continuous. We had weight as continuous, length was continuous, width and depth was continuous, whereas color and quality were categorical. If you remember when we used the as factor at the start. I only have 3 minutes. Let me only explain one part for the case of quality. When you're seeing for the case of quality, if I highlight this particular part, quality we've got good, it was categorical good, ideal, premium, and then very good. But remember in this particular case, there were five levels. We had fair, good, ideal, premium, and very good. Within R can be able to, it can automatically create for you a baseline reference or a reference category, or you can command it yourself depending on how you want to review your result. For example, in this particular case, let me concentrate on the ideal because it is the one that has got a p-value which is less than 0.05 compared to the other variables. So what I can say, because in this particular case, the output that I've got has been fair is the reference category. So I need to explain my result in reference to the fair category. For example, maybe this dealer person, the business dealer in diamond, okay, already knows at the market that the fair diamonds are, they are good when it comes to price. However, we want to recommend that depending on the quality, that I say that with the fair, the quality fair outcompetes the market. But now what about other qualities of diamond? And statistically, we are seeing that the ideal has a p-value of 0.064, which is less than our 0.05, implying that we are going to reject the null hypothesis, whereby it is telling us that alpha is equal to 0.05. So we are reducing the probability of committing an error to 0.006. And now when it comes to the coefficient, as you are seeing that when you're seeing for the case of ideal, it implies that the price for ideal is 2449.36 times more likely to increase compared to the fair price, because we are comparing the ideal to the fair price. And it's the same thing. We are saying that still there is a positive strength on ideal. So as we are comparing, the direction is still positive. So you tell this dealer person that, you know what, as you are looking at fair, it is also good that you can go into you can also consider the diamonds that have got ideal as a quality to also support you as you're competing in the market. My time is up. I want to ask in the chat if that has been clear. Is it okay? Okay, fine. Great. Okay, so given the time that we have, we are going to stop here, and then we'll continue from there tomorrow. I'll have a simple recap, but I also encourage you to get familiar to the data, whatever applies to yours. You also take a quick look on what is happening. And then, Prof, you're sending the link? Okay, then Professor Susan is going to paste here the Zoom link, the support Zoom link, and then we can meet those who still need more explanation or something need to clarify at 2. We're having a support link at 2, and then tomorrow we'll move on to, after recap, we'll move on to model building, such that we are able to understand among the different models that I've developed, which one suits my data very well. Thank you so much. Have a great afternoon. Bye-bye. What are you saying?